Introduction. Engineering begins in the mind. Before an engine roars to life or a bridge spans a river, there's a mind behind the matter. A mind that doesn't just solve problems, but sees them as puzzles waiting to be cracked. This book isn't just about mechanical systems, it's about mental systems. And today, we begin at the very source, your mindset. Let's go beyond textbooks and toolkits. Let's talk about thinking, because the most powerful tool an engineer ever has is not in their hands, but between their ears. Chapter 1. What is the engineer's mindset? The engineer's mindset isn't just about equations and calculations. It's a way of seeing the world through a lens of logic, clarity, and possibility. At its core, it's about three things: being logical, being analytical, and being solution-oriented. It means asking, why is this happening? Followed by, how can I fix it better than before? It's about noticing inefficiencies, breaking down chaos into understandable components, and not being intimidated by complexity, but rather feeling challenged by it. Real-world examples of engineering brilliance. Consider Isambard Kingdom Brunel, one of the greatest mechanical engineers in history. When others saw the River Thames as a natural barrier, he saw it as a problem that could be solved. Result? He helped build the first underwater tunnel beneath a navigable river. Or think about Kalpana Chawla, a mechanical engineer and astronaut. Her work and journey show how the mindset of an engineer transcends borders, both earthly and cosmic. Then there's Elon Musk. Love him or criticize him, his thinking reflects a core engineering trait: don't accept the default. He broke down the cost of rocket launches and asked, what if we built it all in-house? None of these pioneers had just a technical degree. What they had was the mindset to persistently break problems into solvable pieces. The power of systems thinking and reverse engineering. Engineers thrive on systems thinking, zooming out to understand how parts work together before zooming in to optimize individual components. Reverse engineering is the cousin of this concept, taking apart a finished product to see how it works, learning by deconstructing. When we reverse engineer not just machines but our own experiences, we develop resilience, curiosity, and adaptive intelligence. Clarity and structured problem solving. At the heart of every solution is clarity, not just about the answer, but about the problem itself. The engineer doesn't dive straight into solving. First, they define, they investigate, they break a situation into layers. What is the input? What is the process? Where are the variables? What outcome do I want? What constraints exist? This is not just a professional skill, it's a life approach. Mini exercise. Think like an engineer. Let's try something together. Pick one challenge you're facing in your personal or professional life. Maybe you're overwhelmed with your final project, or you're struggling to manage your time. Now pause. Step into the shoes of an engineer. Define the problem clearly. Break it into components. Time, tools, knowledge, motivation. Map out a process to improve each component. Identify one action step you can take for each. You've just engineered your way forward, not with fancy software, but with a structured mindset. Closing thought. This is how engineers think. Not reactively, but proactively. Not emotionally, but systematically. In the chapters ahead, we'll build on this mindset, adding tools, frameworks, and real project strategies. But remember, it always starts the foundation of problem solving. Problem solving is the essence of engineering. It's not about coming up with quick fixes, but finding lasting, innovative solutions that stand the test of time. A great engineer doesn't just apply standard solutions, they look at the problem from every angle, every possibility, every constraint, until they arrive at the most efficient solution. Problem solving, not just a skill, but a mindset. To be an effective problem solver, you need more than knowledge. You need a mindset that allows you to dissect a challenge, reassemble it in new ways, and come up with a solution that meets both functional and creative needs. It's about asking questions like, what assumptions am I making? Are there unseen constraints? And what is the real problem, not just the symptom? Think about how doctors diagnose patients. They don't just treat the symptoms, they figure out the root cause. In engineering, it's no different. By examining the system's behavior, analyzing data, and using both logic and intuition, you break down the problem and generate the best solution. Real-world examples of problem solving. Take Leonardo da Vinci, one of the most brilliant minds in history. Though best known as an artist, his engineering and problem-solving capabilities were groundbreaking. For example, he designed flying machines long before airplanes existed, pushing the boundaries of what was thought possible. Or look at Thomas Edison. Edison didn't invent the light bulb in a single step. He experimented with hundreds of materials and methods before finding the right filament. His persistence, even in failure, shows how engineers approach problems, testing, failing, and ultimately succeeding through iterative processes. Then there's Marie Curie, whose work in radioactivity revolutionized medicine and science. Curie's persistence in pursuing an elusive problem, a problem that many thought was too dangerous to explore, resulted in groundbreaking discoveries that changed the world. Analytical thinking, breaking down complex problems. Engineers don't see problems in isolation. They see the system in its entirety, how components affect one another, and how small changes can lead to large shifts in behavior. The analytical approach involves thinking step by step, breaking down complex issues into simpler elements, and understanding their interconnections. It's like solving a jigsaw puzzle. The final picture might seem daunting at first, but by working on each piece methodically, you begin to see the overall design come together. Engineers do the same by analyzing and testing the small parts of a problem before solving the larger one. Iterative design and testing. A crucial part of problem-solving in engineering is the iterative process. When faced with a challenge, the first solution you try is often far from perfect. The key is to refine and improve through iteration. It's an ongoing process of making small changes, testing those changes, and making more improvements. Consider the development of the modern smartphone. Every new model is an iteration on the previous one, slightly improved but constantly evolving. This iterative process leads to better design, functionality, and user experience. Mini exercise. Break down your challenge into sub-problems. Now let's dive into an exercise. Take the same challenge you worked on in the last chapter. This time, instead of focusing on the overall problem, break it down into smaller, more manageable components. Identify the sub-problems that make up the whole. For example, if you're working on your final project, break it into design, material selection, simulation, testing, and presentation. If you're struggling with time management, break it down into prioritization, planning, distractions, and execution. By dissecting a larger problem into smaller sub-problems, you make it more manageable and approachable. Closing thought. Remember, as an engineer, you are not just a solver of problems. You are an innovator, a creator, a designer. Each challenge you face is an opportunity to improve, learn, and grow. In engineering, no problem is too big. It's just a series of smaller problems waiting to be solved. In the next chapter, we'll explore the process of creativity in engineering, how to unlock the innovative thinking that leads to the next big breakthrough. But for now, think of this. Every problem you solve makes you not just an engineer, but creativity in engineering. Artist. Creativity isn't just for artists, it's for engineers too. In fact, creativity is at the core of engineering. It's the spark that ignites innovation, the ability to think beyond the existing solutions and come up with something new, something better. But creativity in engineering isn't about random ideas. It's about solving real-world problems with clever, efficient, and practical solutions. The role of creativity in engineering. Creativity is not just a buzzword. It's a crucial skill for engineers who want to push boundaries. Engineers are problem solvers, but to be a great problem solver, you need to create new ways of thinking. Creativity in engineering allows you to connect disparate ideas, reimagine conventional solutions, and come up with out-of-the-box answers to tough problems. It's about applying scientific principles, but in new, novel ways. Whether it's a new design, a new material, or an innovative method, creativity turns theoretical concepts into tangible products and solutions. Real-world examples of engineering creativity. Take the example of the Dyson vacuum cleaner. James Dyson didn't just design a vacuum. He revolutionized the industry by creating a vacuum that uses cyclonic separation to maintain suction power. He saw a fundamental flaw in conventional vacuum cleaners and invented an entirely new technology that changed the market. Or think about the development of the electric car. The idea itself isn't new, but it took creative minds like Elon Musk and his team at Tesla to take it to the next level, making electric vehicles viable, desirable, and technologically advanced. Another example, the creation of the modern airplane. The Wright brothers weren't just interested in flight. They were obsessed with understanding the problem from all angles, experimenting with different designs, and improving with every failure until they achieved success. Their creativity turned a dream into a reality. Problem solving meets creativity. So how does creativity work in the context of problem solving? Think of it as a two-step process. One, understanding the problem deeply. You first need to break down the problem and fully understand the constraints, variables, and challenges. This step often involves research, observation, and an analytical approach. Generating multiple ideas. Once you understand the problem, the next step is to brainstorm solutions. The best engineers don't settle for the first idea that comes to mind. Instead, they generate multiple solutions, weigh their pros and cons, and choose the one that's both innovative and practical. The more ideas you generate, the more likely you are to come up with a creative, viable solution. But it's important to know that not every creative idea will work. Failure is part of the process, and creative minds don't fear failure. They learn from it. Harnessing creativity in engineering practice. Creativity can be nurtured. It's not something that only some people have. Every engineer can cultivate their creativity with the right mindset and environment. Here's how. Encourage curiosity. Ask questions constantly. Don't just accept things as they are. Explore why they exist, how they work, and if there's a better way. Learn from failure. Each failure is a learning opportunity. Embrace it as part of the creative process. Collaborate. Creativity often thrives in collaboration. Different minds bring different perspectives, leading to more creative and effective solutions. Give yourself time to think. Innovation doesn't always happen in front of a screen. Sometimes the best ideas come when you step back, think quietly, and let your mind wander. Mini exercise. Brainstorm creative solutions. Let's work on expanding your creativity. Think of a recent engineering challenge you've encountered, whether in school, work, or even a personal project. Now, instead of jumping straight to a solution, spend 10 minutes brainstorming as many ideas as you can, no matter how wild or unconventional they seem. Write down every thought, no matter how impractical it might initially appear. Once you've exhausted your ideas, go back and evaluate them. Are any worth exploring? Is there a common thread that could lead to a viable solution? Sometimes the best ideas come from unexpected places. Closing thought. Creativity is not about waiting for a flash of inspiration. It's about actively cultivating an environment where fresh ideas can grow, nurturing your mind to think differently, and always being open to new possibilities. In the next chapter, we'll look at how engineers use technology and tools to bring their creative ideas to life. But for now, remember this. Creativity is at the heart of engineering. It's not about being given an answer. It's about finding your own. Keep exploring, keep innovating, the power of technology and tools in engineering. In today's world, engineering is not just about what you know. It's about how you apply what you know, often using advanced technology and tools to bring ideas to life. From simulation software to CAD, computer-aided design tools, technology has transformed the way engineers design, test, and build systems. But tools alone aren't enough. It's how you use them that matters. The role of technology in modern engineering technology is the enabler of innovation. It allows engineers to visualize complex systems, simulate real-world scenarios, and optimize designs before they are ever built. With the right tools, engineers can test ideas virtually, save time, and reduce the risk of failure in the physical world. Whether it's 3D modeling, finite element analysis, FEA, or computational fluid dynamics, CFD, technology gives engineers the ability to explore possibilities that were once unimaginable. For example, simulation software can predict how a material will respond under stress, allowing you to refine a design without ever needing to create a physical prototype. But just like creativity, technology is most effective when it's used as part of a comprehensive approach. It's not enough to simply rely on the software. You must understand the underlying principles, know how to interpret the results, and be able to make adjustments based on your analysis. Real-world examples of technology-driven engineering. One of the most powerful examples of technology in engineering is the construction of skyscrapers. Modern architects and engineers use sophisticated modeling software to design buildings that are not only visually stunning, but also structurally sound. Without tools like BIM, Building Information Modeling, these kinds of projects would be incredibly difficult to execute. Think about the design of modern automobiles. Automotive engineers use simulation tools to model everything from aerodynamics to crash testing, improving both the safety and efficiency of vehicles. Companies like Tesla have pushed the boundaries by integrating cutting-edge technology into their design processes, making electric cars not just viable, but desirable. In aerospace engineering, technologies like CFD and FEA have revolutionized the way aircraft and spacecraft are designed. The ability to test materials, airflow, and stress responses before any physical testing takes place has accelerated the pace of innovation, making designs lighter, more fuel-efficient, and safer. Mastering the tools of the trade. To be an effective engineer in the modern world, you need to master the tools of the trade. However, it's important to remember that the tool is only as good as the person using it. Tools are designed to make your life easier, but they don't think for you. For example, CAD software allows you to create intricate designs, but you still need to understand the underlying mechanical principles to create a functional system. Simulation tools give you the ability to predict outcomes, but only if you know how to interpret the results and make decisions based on them. Here are some of the most important tools engineers use today. CAD, computer-aided design. CAD tools like AutoCAD or SolidWorks allow you to design products with precision and efficiency, creating 2D and 3D models. FEA, finite element analysis. This software helps analyze how a material or structure will react under various forces, predicting its performance in real-world conditions. CFD, computational fluid dynamics. CFD tools allow you to simulate fluid flows and thermal properties in systems, optimizing designs for aerodynamics, heat transfer, and more. CAM, computer-aided manufacturing. CAM tools bridge the gap between design and production, automating the manufacturing process to create parts from digital models. The balance between technology and fundamentals. While technology is a powerful tool, it's crucial not to rely on it too much. At the core of every engineering decision lies a deep understanding of the fundamentals: physics, material science, thermodynamics, and mechanics. Technology amplifies this knowledge, but it doesn't replace it. An engineer must always ask themselves, do I understand what the tool is telling me? Can I trust the results, or do I need to adjust my assumptions? When you have a strong grasp of the basics, you'll be able to use technology more effectively and make better decisions. Mini exercise. Explore a tool you've never used before. Now let's put theory into practice. Choose a tool or technology that you've never used before but are curious about. It could be a simulation software, a new programming language, or even a design tool you haven't tried yet. Spend some time exploring it. Watch tutorials, read documentation, or just experiment with it. The goal here is not to master the tool, but to familiarize yourself with it. Get comfortable with the interface and explore its features. Once you've spent some time with the tool, reflect on how it could be applied to your current or future engineering projects. What new possibilities could it unlock? How could it help you solve problems more effectively? Closing thought. Technology in engineering is like a superpower. It amplifies your abilities, expands your horizons, and gives you the tools to tackle bigger challenges. But remember, technology is at its best when paired with a solid understanding of the basics and a creative mindset. In the next chapter, we'll look at how engineers communicate their ideas, because no matter how innovative your solution is, it's only as powerful as your ability to share it with others. Communication is just as essential as technical expertise in bringing your vision to life. But for now, keep experimenting, keep learning, and keep embracing the tools that will help you engineer. The unsung skill of an engineer. You can design the most efficient engine. You can simulate complex systems with advanced tools. You can solve equations most people would never dare attempt. But if you can't explain what you did, clearly, confidently, and convincingly, your idea may never see the light of day. Engineering isn't just about knowing, it's about showing. Communicating your ideas is what bridges the gap between conception and implementation. Why communication matters in engineering. In the world of engineering, communication is more than just speaking or writing well. It's about translating technical complexity into actionable clarity so that teams can collaborate, clients can understand value, and decision makers can trust your judgment. You don't work in isolation. Whether you're presenting your design to a client, writing a project report for stakeholders, or simply coordinating with your team, clear communication is what ensures progress doesn't stall. Think of communication as the user interface of your engineering mind. If people can't understand your ideas, they won't use them. Real-world examples of engineering communication at its best. Consider how NASA shares its complex projects with the public. From launch simulations to mission updates, they use animations, briefings, and visuals to explain advanced aerospace systems in ways everyone can understand. That's not just PR, it's effective engineering storytelling. Or take the example of Steve Jobs introducing the first iPhone. He wasn't an engineer in the traditional sense, but he communicated engineering breakthroughs in a way that connected with millions. He turned microchips and touchscreens into magic through the power of clear narrative. In the corporate world, engineers who rise to leadership positions often do so not because they're the smartest in the room, but because they know how to explain technical ideas in ways others can grasp and act upon. The 3 layers of effective engineering communication. 1. Clarity. Use simple, precise language. Avoid jargon when unnecessary. Explain ideas as if your audience has never seen your work before. 2. Structure. Organize your communication like an engineer solves a problem, step by step. Introduction, objective, methods, findings, and conclusion. 3. Story. People remember stories, not specs. Frame your work in terms of the challenge, the journey, and the result. We had this problem. We explored these options. Here's what we found. Whether it's a thesis, a journal article, a project review, or even an elevator pitch, those 3 elements, clarity, structure, and story, can transform your message from technical noise into impactful insight. Modes of communication. Every engineer should master. Written reports. Learn to write concise, accurate, and well-organized documentation, from research papers to design briefs. Visual communication. Use diagrams, charts, simulations, and CAD renderings to help people see what words can't capture. Verbal presentations. Whether it's to your professor, your team, or your manager, learn to explain your work with confidence and precision. Collaborative feedback. Communication is two-way. Be open to listening, receiving feedback, and asking better questions. Engineering is as much about learning as it is about doing. Mini exercise. Explain a concept. Simply pick one technical concept you've learned recently, maybe stress concentration, laminar flow, or mesh refinement. Now, imagine you're explaining it to a non-engineer friend. Write out or say aloud a short explanation, using simple analogies or visuals. No equations, no jargon, just a clear, intuitive explanation. Can they understand it? Could they explain it to someone else? If yes, you've just practiced one of the most valuable skills an engineer can have. Closing thought. Your ideas are only as powerful as your ability to express them. The engineer who communicates well doesn't just get better grades or promotions, they get their ideas implemented. They inspire trust. They lead. In the next chapter, we'll explore teamwork in engineering, because every ambitious project, from rockets to robots, is built by teams, not individuals. For now, remember, speak with clarity, write with purpose, and always engineer your words as carefully as you engineering is a team sport. No matter how brilliant your ideas, no engineer builds a bridge alone. Every product, every machine, every system you use was made possible not by a solo genius, but by a team of minds working in sync. Engineering is at its core collaborative. It's not about individual brilliance. It's about shared vision, collective effort, and mutual respect. The best engineering teams don't just combine skills, they combine mindsets. Why teamwork is essential in engineering. Engineering projects are rarely confined to a single domain. Designing a wind turbine requires not just mechanical input, but also electrical systems, environmental assessments, manufacturing insights, and logistics planning. That means working with different specialists, each with their own way of thinking, communicating, and solving problems. A successful engineer knows how to integrate, not dominate. They know how to contribute their strengths while drawing on the strengths of others. That's the key to real innovation. building systems that are greater than the sum of their parts. Real-world examples of engineering teamwork. Take the Mars rover missions. Hundreds of engineers, scientists, designers, and analysts worked for years to send a vehicle to another planet. It wasn't just about rockets and code. It was about coordination, collaboration, and trust across continents and time zones. Or think about Formula One racing teams. The speed you see on the track is the result of teamwork in the pits, the design lab, the simulation suite, and the control center. When everyone works together seamlessly, performance soars. Even in college design projects or startup environments, the teams that communicate openly, assign roles clearly, and respect each other's input always outperform those that don't. Key ingredients of effective engineering teams. 1. Shared goal. Every member needs to know the why. When the goal is clear, the group moves in the same direction. 2. Defined roles. Clarity in who does what prevents overlap, confusion, and frustration. Everyone knows their zone and respects other zones too. 3. Open communication. Teams that talk openly and regularly solve problems faster. Issues surface sooner. Ideas evolve more creatively. 4. Mutual accountability. Great teams hold each other to high standards, not out of pressure, but out of pride in their shared mission. 5. Respect for diversity. Engineers from different cultures, genders, or backgrounds bring different perspectives. Embracing that diversity leads to stronger, more inclusive solutions. Collaborative tools for engineers. Today's engineering teams rely heavily on digital collaboration tools. Version control systems like Git to manage code or design changes. Cloud-based CAD platforms to co-design in real time. Project management tools like Trello, Jira, or Asana to track progress. Shared simulation environments to test, tweak, and align designs. Communication platforms like Slack or MS Teams for constant feedback and updates. But remember, tools are only as good as the trust behind them. A well-organized folder won't save a poorly aligned team. Mini exercise. Reflect on a team experience. Think about the last time you worked in a group, maybe on a project, a lab, or even an extracurricular event. Ask yourself, what worked well? What caused friction? Did everyone know their role? Was feedback welcomed or avoided? If you were to lead that team today, what would you do differently? This kind of reflection helps you become not just a better teammate, but a future team leader. Closing thought engineering is not a solo journey. The biggest breakthroughs are team-built. Learn to listen, to lead, to support, and to sync. The better you are at working with others, the farther your ideas will go. In the next chapter, we'll explore how engineers think in terms of time, planning ahead, working backwards, and managing resources wisely. Because great ideas need timelines, milestones, and strategy to become real. For now, honor your team, appreciate the process, and remember, time thinking. We build better engineering with the clock in mind. Every project has a deadline. Every machine operates in cycles. Every system has a timeline. As an engineer, time isn't just a constraint. It's a dimension you must learn to work with. Great engineers don't just design products, they design processes. They don't just solve problems, they schedule solutions. Thinking in time, planning, pacing, and prioritizing is what separates reactive students from proactive professionals. What is time thinking? Time thinking means understanding how long things take, how tasks depend on each other, and how to adjust when timelines shift. It's both strategic and tactical, from visualizing project milestones to knowing when to stop perfecting and start delivering. Think of it like this: a brilliant design delivered too late is just as ineffective as a flawed one delivered on time. Your goal isn't just quality, it's timely quality. Real-world applications of time thinking. Look at how Boeing schedules the development of a new aircraft. It's not just about design. It's about integrating design, testing, manufacturing, certification, and delivery, each with timelines that affect the others. A delay in one area can cost millions. Or consider a Formula student team working on their car. They only get one season. If they spend too long in the design phase, they have no time left to test. So they work backward. When's the race? Then they map out everything that needs to happen before that day. Design, fabrication, testing, revision, logistics. In the real world, engineering is ruled by time. If you master your calendar, you master your career. The Engineer's Time Toolkit 1, Gantt charts. A simple, visual way to map out tasks across a timeline. perfect for seeing dependencies and overlaps in a project. 2. Critical path method. Identify which tasks are time sensitive and which have slack. Focus your energy where delays would be most costly. 3. Time buffers. Always add a buffer. Unexpected issues always arise. Your plan should expect the unplanned. 4. Milestones. Break big projects into meaningful checkpoints. This helps track progress and keeps morale up. 5. Time boxing set fixed amounts of time for specific tasks. This prevents perfectionism from becoming procrastination. Time thinking in design and simulation. In simulation-based projects, time management becomes even more crucial. Mesh generation, solver runtimes, data analysis, these all consume time, often in unpredictable ways. Knowing when to run a coarse mesh to test logic versus when to refine for accuracy can save you hours or days. Learn to set up automation for long runs, plan simulations overnight, and analyze results during idle times. Make the computer work while you sleep, and always have a backup plan if a simulation fails. Mini exercise. Reverse engineer your next deadline. Pick a current project or assignment. Step 1, write down the final deadline. Step 2, list every major component required to complete it. Step 3, estimate how long each part will take. Step 4, build a mini Gantt chart or timeline on paper. Step 5, identify the critical path, the tasks that cannot slip. Step 6, add a 10% buffer. Now you've just engineered your schedule, not just hoping it'll work, but planning it like a system. Closing thought time is not your enemy. It's your framework. The best engineers don't rush and they don't delay. They pace, they sequence, they anticipate. Engineering is not just about making things work. It's about making them work on time. In the next chapter, we'll explore how engineers use feedback, both from systems and from people, to refine, improve, and evolve their work. Because no design is ever perfect on the first try, and the smartest engineers know that iteration is where feedback is the engineer's secret weapon. Here's a truth every great engineer knows. The first version is never the final version. Engineering is not about one-time perfection. It's about iteration. And what powers that iteration? Feedback. Whether it's a stress test failing in simulation, a prototype vibrating too much, or a teammate offering a different perspective, feedback is gold. It's not a judgment of your skill, it's a map to your next improvement. What feedback really means in engineering. Feedback isn't just something you get from others. In engineering, it's a built-in loop. You build, you test, you learn, you improve. Think of it as a signal. A vibration reading is feedback. A simulation error is feedback. A client's confusion about your design is feedback. It tells you where your system is misaligned, so you can realign it. And the earlier you seek it, the better. Waiting for perfection before showing your work leads to waste. Early feedback saves time, resources, and reputations. Real-world feedback in action. Take structural testing in aerospace. Engineers build scale models and subject them to wind tunnel tests, thermal stress, vibration tests, all before production. Why? Because every anomaly they catch early prevents a costly or dangerous failure later. Or consider agile development in product design. Instead of designing everything up front, teams release small, testable pieces and get real-world feedback. That input shapes the next version and the next, until the system is not just functional, but optimized. Even in academic projects, feedback from advisors, mentors, or peer reviewers can transform a mediocre idea into a publishable paper if you're willing to listen. The Feedback Loop Model 1. Design start with your best understanding of the requirements. Build version 1. 2. Test, simulate, prototype, or share your work, whatever generates data or reaction. 3. Analyze. What went wrong? What surprised you? What did others notice that you didn't? 4. Improve. Make adjustments, then cycle again. This loop, design, test, analyze, improve, is the engine of every great engineering solution. Giving and receiving feedback. Engineers must be fluent in both directions. Giving feedback, be specific, be constructive, and focus on the system, not the person. Receiving feedback, don't defend. Don't explain it away. Listen. Ask clarifying questions, then decide how to act on it. Great teams thrive on feedback culture. It builds trust, speeds up iteration, and makes every member smarter. Mini exercise, build your own feedback loop. Pick a piece of work you're currently developing, a simulation, a CAD model, a research write-up. Step 1, share it early with a peer or mentor. Step 2, ask them to point out 2 things. what's unclear, and what could be improved. Step 3, thank them. Don't explain, just listen. Step 4, apply the feedback. Step 5, repeat in 2 days with the improved version. This practice builds a muscle and makes your work better, faster. Closing thought: feedback isn't failure, it's forward motion. The best engineers are not the ones who get everything right the first time. They're the ones who learn faster than the rest. In the next chapter, we'll explore innovation, how engineers go beyond solving problems to creating new possibilities. Because once you master the mindset, the tools, the teamwork, the time, and the feedback, innovation, your next step beyond solving, toward creating. Engineering begins with solving problems, but it thrives in creating possibilities. Innovation is not just about new gadgets or flashy tech. It's about rethinking what's possible, seeing gaps others ignore, and applying knowledge in ways no one has dared to before. As an engineer, innovation is your opportunity to leave fingerprints on the future. What innovation really means in engineering. Innovation is when logical thinking meets imaginative vision. It's not just invention, building something entirely new. It's also about refinement, making existing systems better, faster, cheaper, or more sustainable. Engineers innovate when they combine technologies from different fields, challenge the way things have always been done, solve old problems in new environments, apply simplicity to complexity. Innovation isn't always about doing more. Often it's about doing smarter. Real-world engineering innovations. Think about James Dyson. He didn't invent the vacuum. He re-engineered it, removing the bag, adding cyclonic separation, and obsessing over airflow. It took over 5,000 prototypes. That's innovation. Or look at engineers designing portable water purification systems for remote villages. They're not just building machines, they're engineering hope, access, and health. Even in automotive design, switching from internal combustion to electric propulsion required engineers to reimagine energy, storage, cooling, and user experience. That shift wasn't just technical, it was visionary. The ingredients of engineering innovation. 1. Curiosity. Innovators ask, what if and why not? They observe what others overlook. 2. Constraint limits spark creativity. Budget constraints, material shortages, or environmental regulations often push innovation forward, not hold it back. 3. Iteration. Innovation rarely happens in one big leap. It's built step by step through prototypes, tests, and refinements. 4. Cross-pollination. Big breakthroughs often come from combining insights from different domains, like bio-inspired design in robotics or nature-based cooling systems in buildings. 5. Purpose. Innovation with a mission to save energy, reduce cost, improve lives tends to have more staying power than flashy but shallow inventions. Tools that encourage innovation. Brainstorming sketchbooks. Draw out wild ideas without fear. Reverse engineering. Disassemble a product to see what can be improved. Simulation software. Try variations quickly without physical risk. TRIES method. A Russian-born framework for creative problem solving. Design thinking. A human-centered approach to understanding problems deeply before solving them. Mini exercise. Invent within your current project. Take your current project, academic or personal. Step 1. Identify one component that could be better. Step 2. Ask, how else could this be done? List 3 alternate ways. Step 3. Look outside your field. What do other industries do? Step 4. Sketch a revised version, combining one new idea. Step 5. Ask for feedback, then refine. Congratulations. You just took your first steps as an innovator, not by building something wild, but by daring to think differently. Closing thought. Innovation isn't just a skill. It's a habit. It grows every time you resist complacency and choose curiosity. Every time you say, let me try a new approach, you step closer to transforming the world, not just studying it. In the next chapter, we'll bring it all together. Mindset, time, teams, feedback, and innovation into a complete project cycle. Because the true test of engineering isn't what you know. Engineering the project journey from idea to impact. An engineer's true strength isn't just in knowledge, it's in execution. Ideas are powerful, but turning them into reality is where engineering earns its name. Whether you're building a thesis, designing a product, or simulating a system, the project journey is where every skill you've developed comes alive. The phases of an engineering project. Every project, big or small, moves through a similar flow. Think of it as a living system with inputs, processes, feedback, and outputs. Here's how the journey unfolds. 1. Define the objective. Start by asking, what problem am I solving? Why does it matter? Who benefits? 2. Research and benchmark. Study what's already been done. What works? What doesn't? Where is the opportunity to innovate? 3. Ideation and concept development. Sketch multiple ideas. Explore creative options. Don't jump to the first solution. Think wide before you think deep. 4. Design and planning. This is where your CAD tools, simulations, and technical diagrams come in. Define dimensions, tolerances, materials, and process flows. 5. Simulation and validation. Use tools like FEA or CFD to test your design virtually. Identify weak points before building. 6. Prototyping or implementation. Turn your design into something tangible. Even a small-scale prototype gives vital feedback. 7. Testing and iteration. Measure performance. Adjust. Improve. This is your engineering feedback loop in action. 8. Documentation and reporting. Record your process clearly, your methods, results, and learnings. Good documentation is as valuable as the final result. 9. Presentation and delivery. Communicate your work confidently. Whether it's a viva, a client pitch, or a journal article, your voice carries your vision. Real-world application. From concept to launch. Let's say you're building a smart irrigation system for farmers. Define. You want to reduce water waste using sensors. Research. Explore existing products, climate data, and farming needs. Design. Sketch layouts for moisture sensors, power systems, and data logging. Simulate. Use software to model soil moisture diffusion and energy usage. Prototype. Create a working unit with microcontrollers and sensors. Test. Try it in different soil types and refine the logic. Document. Log every component, every test result, and every tweak. Present. Build a slide deck, a demo video, or a working model to showcase your impact. Tools for project execution. Gantt chart, project timeline, bill of materials, component listing, technical report template, simulation analysis spreadsheet, risk and mitigation plan, design review checklist. These aren't just documents, they're your control panels for progress. Mini exercise. Map your current project phase. Think of your current academic or personal project. Step 1. Identify which phase you are in right now. Step 2. Write down what your next immediate step is. Step 3. Identify what resource, time, tool, feedback, clarity you need to move forward. Step 4. Take one action today that moves you closer to completion. Closing thought projects are the ultimate test of an engineer's mindset. They demand logic, structure, creativity, and persistence, all at once. But more than anything, they prove this, that the world can be shaped by those who think systematically, plan realistically, and act consistently. In the final chapter, we'll explore what it means to carry this mindset beyond academics into careers, industries, and lives shaped by engineering. Because the journey doesn't stop here. Engineering a legacy, shaping the future with your mindset. As we reach the final chapter, we reflect not just on the knowledge we've built, but on the mindset that drives everything forward. Engineering isn't just a career. It's a mindset you carry with you throughout life, one that turns challenges into opportunities, complexity into clarity, and ideas into impact. But here's the big question. How do you take this mindset beyond your studies, beyond the classroom, and into the world? The power of continuous learning. In engineering, the journey is never truly finished. Technology, materials, and methods evolve, and so must you. As soon as you solve one problem, there's always another to solve. But that's what makes engineering so powerful. There's always room to grow, to learn, and to innovate. Engineers who stop learning aren't just outpaced by progress, they become irrelevant. But engineers who continue to develop, adapt, and challenge themselves stay at the cutting edge. They bring fresh perspectives to old problems and turn new obstacles into stepping stones. From theory to practice, making an impact. When you step into the workforce, the difference between success and stagnation often lies in the practical application of your knowledge. Engineering isn't about theoretical solutions. It's about creating real-world impact. It's about transforming concepts into products, data into designs, and solutions into systems. Whether you're working on renewable energy systems, designing automation for manufacturing, or developing AI-driven algorithms, your role is to apply your training in a way that improves people's lives, makes processes more efficient, or enables new possibilities. The engineer's legacy. It's easy to get caught up in the day-to-day grind, but every engineer has the potential to leave a lasting legacy. Think about how the inventions of Nikola Tesla or the designs of Gustav Eiffel continue to shape the world today. Your legacy doesn't have to be on the same scale, but it can still have a significant impact. Whether it's in your community, your company, or your field of expertise, you have the power to make a difference. Engineering isn't just about solving problems, it's about solving the right problems. And that starts with understanding what matters, both to you and to the world around you. Engineering a better tomorrow. As engineers, we have a unique responsibility to build systems and solutions that not only advance technology, but also benefit society. It's not enough to be a skilled engineer. You must also be a responsible one. Think about sustainability, ethics, and the greater good in every project you tackle. Whether it's reducing carbon footprints, designing for accessibility, or ensuring safety in critical systems, every choice you make can contribute to a better, more equitable world. The road ahead. Engineering your future. The future of engineering is wide open. There will be new challenges, new technologies, and new frontiers. As an engineer, you are always positioned at the forefront of innovation. But to stay there, you must continue to think critically, stay curious, and embrace the unknown. You might design the next generation spacecraft, develop life-saving medical technologies, or revolutionize transportation systems. Whatever path you choose, remember this: your mindset is the key to unlocking your potential. Closing thought: the engineer's journey never ends. In engineering, the destination is never truly the goal. The journey itself is where the magic happens. Your mindset, your approach to problem solving, and your relentless pursuit of improvement will define the projects you work on, thus the teams you collaborate with, and the legacy you leave behind. So as you embark on your journey, whether it's in academia, industry, or entrepreneurship, carry this mindset with you. Think critically, act systematically, learn continuously, and above all, create. Because the world needs engineers who are not just solving problems, but building a better future. Thank you for joining me on this journey. The real work starts now. And remember, the engineer's mindset is not just for today, it's for life. Keep engineering, keep innovating, keep thinking.